Okay, this is chapter 5, and we're going to begin with quantum numbers. Quantum numbers, N and L. There's also M and S. I'll do some quantum number examples at the end. Just two, I think would be plenty. But the two most important quantum numbers for your exam will be understanding what N is. That's the energy level. In other words, if this is a electron configuration, 1, 2, 2, 3, 3, 4, that's the principal quantum number. That's the energy level. And this is the L, that's the shape. Now, the shape, S is a sphere. Sphere, that's two-dimensional, but it's a sphere, three-dimensional. And the P is like a dumbbell shape. It's an odd shape. Now, there's only one S shape, and that's a sphere. Now, P is like a dumbbell shape, but you can have an X, a Y, and also a Z. Remember, there's three P's, right? There's three P suborbitals. Do you remember from, you have three, remember? 1, 2, 3, X, Y, Z. Okay, so you have one in the X direction, one in the Y direction, and then one in the Z direction. Okay, now, so that's going to be the most important thing relative to quantum numbers. Let's erase that, okay? Let's erase that. Now, quantum numbers. All right, and again, we'll do some practice quantum numbers at the end. Next thing, electron configuration. For instance, this is iodine, 127 and 53. So it would be 1s2, 2s2. Follow along on a periodic table. 2p6, 3s2, 3p6, 4s2, and then 3d10, 4p6, then 5s2, 4d10, and then 5p5. Follow along with a periodic table for that. Okay, so you need to know electron configurations. You also need to know if you have the short form. For instance, strontium, copper, and chromium. These are short form electron configurations where you start with the noble gas. The nearest noble gas to strontium is krypton, the nearest preceding noble gas. And then you know that it's in group 2, and you know it's going to be 5s2. Copper, argon, 4s1, 3d10. Why did I say that? Why didn't I say copper, 4s2, 3d9? And chromium, 4s1, 3d5? I don't understand. Well, they're exceptions, but really not exceptions. And the reason is down here. Here is chromium. 4s2, let me get on this side. 4s2, and then 3d4. That's what you would think. Chromium, it's in the fourth over, the fourth d over. Look at chromium, look at a periodic table. And it actually becomes, this one electron goes up and makes that a half-filled D. Now, what that makes is, this is lower energy to higher energy. When you write these, you write them from low to high energy. Okay. So what happens is the D, now it's 3D5. Okay, this is 3D5. That's actually a little bit lower energy. So you have 4s1 and then 3d5. okay? But it's actually 3d5, 4s1. So this is actually not correct. It's not correct. Because when you write electron configurations, you write from the lowest energy to the higher energy configurations. So this would actually be, let's look at copper. Copper would actually be argon, and then 3d10 would be more stable, would be a lower energy level than the 4s1, and then you would write 4s1. But that's kind of splitting hairs a little bit. But if on a multiple choice test they give you that as a choice, then that's actually correct. Okay, and then chromium would be 3d5, 4s1. So when you write these out like this, these electron configurations, you're writing it from the lower energy state to the highest energy state. So when you're writing this, you're writing it from the lower energy state, all the electrons up to and including argon would be lower energy than these. And then because you get this sort of hybridized state, then you get these are actually lower energy than that. So you could actually argue that it would be 3d5, 4s1. Okay? So, now, remember, a full shell is most stable, but a half shell is very stable as well. It's stable. Let's not say it's very stable, but it is certainly stable. So that's why you get this drive for this half filled in terms of chromium. Okay? So let's erase that. Okay? Erase that. Erase that. And then let's see, what else? Let's do this. Let's do this. Here I have 4 ions. That's a cation, anion, anion, cation. How many electrons are in each of those ions? Well, it's not ground state. It's not protons equals electrons. That's not the case. We know this has 20 protons, but it's going to give up 2 electrons to be like the nearest noble gas, which would be argon. So this has 18 electrons, and it would be like argon. That would be the quote-unquote noble configuration. Chlorine would be, I'm looking up here, would be the same thing. This would be 18 electrons. Remember, 17 protons, 17 electrons if it's ground state. But it's getting that extra electron because it's negative, so it's going to be like argon. And then bromine is going to be like krypton. It'll be 36. It'll be like krypton. And then sodium will be, it's going to give up an electron because it has 11 protons, 11 electrons, but it's going to give up an electron to be like neon. So it'll have 10 electrons, and it'll be like neon. Like neon, it won't be neon, obviously. Okay? So let's get rid of that. Okay? Easy? We'll get rid of this. We'll get rid of this. We'll get rid of this. And all we're left with is this. Let's say I have a photon with an energy of 7 times 10 to the negative 23 joules. Joules is a measure of energy. It has Planck's constant, which is a constant, Planck's constant, which is 6.6 times 10 to the negative 34 joules times seconds. And then the equation is E equals h nu. Looks like V, but it's really not. It's the Greek letter nu. It means frequency. So I want to solve for frequency. So I'm going to say frequency nu equals E over h. Plug in 7 times 10 to the negative 23rd joules from here, divided by 6.6 times 10 to the negative 34 joule seconds. And put that in your calculator, and you'll get 1.1 times 10 to the 11th hertz. Make sure you can do those calculations. Do some practice ones, practice putting them in your calculator, etc. Okay? So that's finished.